Hello everyone. Today I'm going to present my paper, a generalized apprenticeship learning framework for modeling heterogeneous student pedagogical strategies. I am the presenter, I'm the Mirajul Islam, and the other authors, John Hostetter, Adittya, Soukarjya, Saha, and Dr. Binchi. We are from North Carolina State University, and Shi Yan is from IBM Research. Pedagogical strategy lies in the heart of success for intelligent tutoring systems, where the ITS is an adaptive e-learning system that imitates human tutors and aims to provide immediate and customized instruction or feedback to learners. On the other hand, pedagogical strategies are policies to decide which pedagogical action to take in the face of alternatives. Reinforcement learning and deep reinforcement learning have shown great promise in modeling pedagogical strategies. But deep reinforcement learning needs a lot of exploratory data to induce effective pedagogical policy. Another problem is manually designing an appropriate reward function is difficult and can be misspecified. That is why our solution is based on apprenticeship learning, or AL, which is learning by observing and imitating expert agents. So for our case, the goal is to learn from students making decisions, only those who are good at making decisions. There are few works where the apprenticeship learning has been applied in the education domain. For example, behavior cloning, maximum entropy inverse reinforcement learning, adversarial imitation learning, and expectation maximization based IRL or EMIRL has been applied to subtype students from their pedagogical behavior data, but that can only handle discrete state representation. Another state-of-art AL method, energy-based distribution matching, EDM, has been very successful in inducing effective policies, which assumes demonstrations are generated using a single reward function, but students may have different reward functions. We have proposed EM-EDM, which is a general AL framework to induce effective pedagogical policies from given optimal or near optimal demonstrations, which are assumed to be driven by heterogeneous reward functions. So EM-EDM is data efficient, can handle large continuous state space, and assumes multiple heterogeneous reward functions. To evaluate the effectiveness of EM-EDM, it was compared against two policies induced by DRL using 2000 student ITS interpreter trajectories, respectively, and 4 AL-based baselines using only 53 expert trajectories on two student pedagogical action prediction tasks, which is very challenging. And the results show that EM-EDM outperforms all the chosen baselines. In summary, the contribution of EM-EDM is EM-EDM can effectively model complex student pedagogical decision-making process and manage a large continuous state space and handle diverse and heterogeneous reward functions. The empirical evaluation of EM-EDM actually compares 4 state-of-art L baselines and 2 DRL baselines on 2 significant tasks, and the results obtained from EM-EDM shows that students' demonstrations exhibit heterogeneous reward functions and can induce distinct pedagogical policies for different reward functions, even with as few as 24 demonstrations. This is the outline of my rest of the presentation. Beginning with the introduction, reinforcement learning is a type of machine learning where an agent learns to make decisions by performing actions in an environment to maximize some notion of cumulative reward. Here, the goal is to learn a decision-making policy that aims at benefiting students by maximizing the cumulative rewards in the long run. Deep neural networks has enabled significant progress in oral research, but it has some obstacles like sample inefficiency and reward function design difficulty. From that point of view, apprenticeship learning aims at learning by observing and imitating a few demonstrations provided by expert agents who make decisions optimally or near optimally with respect to an unknown underlying reward function. AL approaches can be either online or offline. In online manner, agent learns while interacting with the environment, and in offline scenario, agent learns from pre-collected data. For our given scenario, we focus on offline AL. Here are some of the related works of apprenticeship learning. Here we can see like behavior cloning, maximum entropy inverse reinforcement learning, generative adversarial imitation learning, and adversarial inverse reinforcement learning. All of them algorithms actually assumes a single reward function, as well as the state-of-art energy-based distribution matching, EDM. There is one algorithm listed in this grid, which is expectation maximization based IRL, that assumes multiple reward function, but that cannot handle the continuous state space. On the other hand, there are some algorithms which can handle both discrete and continuous state space, but they do not assume multiple reward function. So here we come and propose our method, which is EM-EDM. Before we go to EM-EDM, we would like to give a little description of the EDM. So energy-based distribution matching jointly learns the policy function with an energy-based model of the state distribution, which minimizes a divergence between occupancy measures for demonstrator and imitator. So here you can see the probability density for each state action pair and the probability density for each state. So the goal is minimizing the pullback labor or KL divergence between the occupancy measures of demonstrator and the learned policy. Since the probability of taking action A in state S under the policy pi theta is proportional to how frequently the state action pair SA is visited relative to how frequently the state S is visited, we can reformulate the objective function as the following in equation 2. So energy-based model is a type of probabilistic model used to represent the dependencies between variables. Here we can see, according to the energy-based model, the probability density of a variable S can be represented as the following, like it is proportional to the exponential of some energy function. The occupancy measure for state action pairs can be represented as follows, as well as the occupancy measure for states, where the Z is a partition function or normalization constant, which ensures the probability is sum to 1. The parameterization of pi theta implicitly defines an energy-based model over the state distribution, where the energy function can be defined as the following. Thus, the first term in equation 2 can be reformulated as an occupancy loss, and here we can derive a surrogate objective function, which combines the policy loss function and the occupancy loss function. So this is the final objective function we aim to minimize. Here comes the proposed method, EM-EDM. So the EM-EDM method take trajectories as input, with n being the number of trajectories. EM-EDM aims to cluster these trajectories and learn the cluster-wise policies, where k is the number of clusters, Vj and theta j denote prior probability, and the policy parameter of each cluster, and both are randomly initialized. The objective function of EM-EDM is to maximize the log likelihood defined in equation 4, you can see, where Uij defines the probability that trajectory I follows the policy of the J cluster. It is defined in equation 5 with U being a normalization factor here. So during the EM process, at first, we are getting the input trajectories, which is actually the state action pairs. So we can have several trajectories which are driven by different reward functions. And in the EM process, in the E step, the probability that the trajectory I belonging to cluster J is calculated by equation 5. And then in the M state, the prior probabilities are updated via Vj equal to Pi into Uij divided by N. And the policy parameters theta j is learned by EDM. The E step and M step are iteratively executed until converged. Finally, the output of EM-EDM is clustered trajectories with their respective policies. So now comes the experiment setup. We gathered our data, letting undergraduate students from the same major and same year complete an online intelligent tutoring system that introduced them to probability concepts like bias theorem and addition theorem. All students followed the standard textbook pretest training and post-test process. The dataset size was 128 students from 2 different semesters. From spring 21, there was 67 students, and from spring 22, there was 51 students. And here is a snap of the ITS. The state and actions, like there were 142 continuous state features that were extracted from the student system interaction log data. So these state features can be grouped into 5 different categories. First is autonomy, the amount of work done by student, such as the number of elicits since the last L. The temporal features can be time-related information about the student's behavior, such as the average time per step. The problem-solving features have the information about the current problem-solving context, such as problem difficulty. The performance features have information about the student's performance so far, such as the percentage of correct entries, and the hints features have information about the student's hint usage, such as the total number of hints requested. And the action space we can have three different pedagogical actions: PS, WE, and FWE, which is problem solving work example and faded work example. So in AL, it is typically believed that the experts are performing the demonstrations in an optimal or near optimal manner. To select higher quality trajectories from all student interactions with the ITS, we use a qualitative measurement called quantized learning gain, QLG, which is a binary qualitative measurement of students' learning gains from the pretest to post-test to determine whether a student has benefited from a learning environment. To calculate the QLG, first, the students were split into low, medium, high performance groups based on whether they scored below the 33rd percentile, between the 33rd and 66th percentile, or higher than that in pretest and post-test respectively. Student is a high QLG if he or she moved from a lower performance group to a higher performance group from pretest to post-test, or remained in high performance groups. Whereas a low QLG is assigned to the student if he or she either moved from a higher performance group to a lower performance group, from pretest to post-test, or stayed at a low or medium groups. So for DRL baselines, we chose conservative Q-learning, CQL, known for addressing overestimation issues in comparison to various existing RL methods, including deep Q-learning, which is extensively explored in prior DRL studies within ITS. So another baseline was CQLT, where CQL's reward function is based on the student's normalized learning gain, which measures their learning gain irrespective of their incoming competence, as well as also that consider the time spent on the tutor. And then in the experimental setting, we had another 4 other apprenticeship learning baselines, which are behavior cloning, generative adversarial imitation learning, or GAIL, AIRL, EDM, and we compared our proposed EM-EDM. The experimental task we evaluated on, there are 2 tasks. The first task is conducting training and evaluation of all the methods for pedagogical action prediction through 5-fold cross-validation, utilizing all 53 selected demonstrations. And the task 2 was conducting training on a previous semester data, which was 24 demonstrations, and evaluating on a subsequent semester data, which was 29 demonstrations. So here comes the result. For task 1, we can see across all the baselines, including the principal learning and apprenticeship learning, EM-EDM outperform all other baselines. And here you can see the metric we considered: accuracy, recall, precision, F1 score, AUC, which is area under the RAC curve, APR, area under the precision recall curve, and J-curve score, which is used to assess the similarity between the predicted set and true set of labels, calculated by size of the intersection divided by the size of the union of 2 label sets. And we also use critical diagrams, or CD diagrams, critical difference diagrams, to visualize the difference of the performance of the classifiers, where the positions of the model represents their mean ranks according to the corresponding metric across the all folds, where high ranks indicate that a model wins more often than its competitors with lower ranks. 2 or more models are connected with each other if we cannot tell their performance apart in the sense of statistical significance with a confidence level of 0.05. Here is the result of task 2, which is future students' pedagogical action prediction. We can see here as well, EM-EDM outperform all other AL baselines and DRL baselines. And here we present the cluster assignments, according to the EM-EDM. We can see, for all the 5 clusters we have discovered, how many students from Spring 21 fall into each of the cluster, and how many students from Spring 22 falls in each of the cluster. In conclusion, EMEDM can effectively model complex student pedagogical decision-making processes through the ability to manage a large and continuous state space and its adaptability in handling diverse and heterogeneous reward function. The results obtained from EMEDM showed that the students' demonstrations exhibit heterogeneous reward function, and it can induce distinct pedagogical policies for different reward functions, even with as few as 24 demonstrations. In future, as a future work, we plan that we will investigate the evolving reward function across demonstrations. And the project has been funded by several NSF projects, as well as a particular project named Engage AI Institute. So thank you all for listening to my presentation. If you have any questions, please feel free to ask. Thank you so much.